Hello everyone, welcome to today's tutorial on signal upsampling and downsampling methods in MATLAB. I'm Shanti. I work as a senior online course developer here at MathWorks. You may know us as makers of MATLAB and Simulink, which are our core products. MathWorks is a leading developer of mathematical computing software for engineers and scientists. Here are some industries where our tools are being used extensively: aerospace and defense, automotive, industry machinery, energy production, and communication, to name a few. In this session, we'll begin with an engineering problem related to signal sampling. We'll discuss why resampling is required and what the effect will be if an improper technique is used for sample rate conversion. Next, we'll see how to solve the engineering problem we have. And as part of this, we will first get started with MATLAB Online, available for this NPTEL course. Then we'll implement the solution using MATLAB Online through a series of hands-on activities. We will use concepts like downsampling, upsampling, and arbitrary sampling to solve the engineering problem we have. We'll end the tutorial by summarizing the key takeaways and with a Q&A session. If you have any questions, please post them in the chat and we will try to address them then and there. We can also discuss the remaining questions during the Q&A session. Here, I would like to emphasize that today's tutorial is focusing on using MATLAB to resample signals without going deep into theoretical concepts. So, discussing about the engineering problem we have today to tackle with is our central question is how we can convert audio signals between different sample rates without introducing distortion or artifacts, with ensuring efficiency and high fidelity. So this is the engineering challenge or problem we will have to tackle today in MATLAB. To explore this, we'll look at three common scenarios of resampling. First is downsampling a signal, where we reduce the sampling rate while ensuring that aliasing is eliminated through proper filtering. Second scenario we will discuss is about upsampling a signal, where we increase the sampling rate and use filtering to suppress unwanted spectral images. And finally, the third concept, arbitrary resampling, where we convert between non-integer sample rate ratio. For example, if we want to convert a signal of having 48 kHz sample frequency to 44.1 kHz sampling rate frequency, and the resampling to ensure compatibility across different audio systems. So this is the engineering problem we are trying to solve today. And before solving this problem, it is important to understand what is resampling is and why we need to resample signals. So resampling is a process of changing the sampling rate of a signal. The number of samples taken per second is called the sampling rate. And this sampling rate directly determines how much frequency information can be captured. So we all know that according to Nyquist-Shannon sampling theorem, the sampling rate must be at least twice the highest frequency present in the signal to avoid aliasing. So what is the need for resampling signals? So there are various instances where resampling is important. For instance, let's consider a scenario of audio production. So for example, recordings often come in different sampling rates in an audio production scenario. So a higher rate like 48 kHz captures more detail and is common in professional studio recordings. But in some cases, the legacy archives might exist at much lower rates, let's say 16 kHz. So this limits the captured frequency component, but was sufficient for older storage and transmission systems. And scenarios where like we have consumer formats like CDs, which uses 44.1 kilohertz, a standard chosen to cover the entire audible range while balancing storage requirements. So these differences in the frequencies, like we have captured audio signal at 48 kilohertz, and we have some devices which is operating at 16 kilohertz, and we have some consumer distribution formats like CDs, which is operating in 44.1 kilohertz. So these differences in sampling rate mean that audio engineers or a researcher or even a system designer must frequently convert one sample rate to another. So this is a need for resampling signals. So while resampling the signal, there is a challenge involved here. So the challenge is here what happens if we do resampling with an improper sample rate conversion ratio or technique. What if resampling isn't done correctly? What happens? So it can introduce noticeable and often distracting artifacts in the resampled audio signal, which will affect the audio quality at the end. So there are various issues while having like improper sampling rate conversion. One common issue is aliasing. So the aliasing is where high frequency components fold back into the audible range and cause distortion. And another problem is imaging. So which occurs after resampling, like after we increase the sampling rate from a lower sample rate to a higher sampling rate frequency, it occurs that there is a problem of imaging in the upsample signal. So what is imaging? It results in unwanted frequency components appearing in the signal, like as images, as spectral images. Finally, the issue can be of poor filtering or even rounding errors can lead to loss of fidelity, degrading the overall quality of the audio. So this highlights, all these issues highlights or challenges highlights why careful signal processing and proper filtering is essential whenever we change the sampling rate. So this is the engineering problem we are trying to tackle today. So the steps involved to find a solution for our engineering problem is the solution approach for solving the engineering problem is broadly divided into four steps. On a high level, four steps is involved in the solution to this engineering problem. So first is to generate the audio signal. And the next is to determine the conversion ratio. What is the conversion ratio between the original sample rate and the target sample rate we have? And the third step is to resample the signal without applying a filter and analyzing the results. So we will see how filtering is important while resampling signal and analyze the results without filtering. Now, as a final step to refine our results, we will resample the signal with appropriate filter selection and see the difference in the signal spectrum before filtering and after filtering. So these are the four broader steps we'll try to implement today in MATLAB to solve our engineering problem of sample rate conversion. As a first step to solve our engineering problem, we'll get started with MATLAB Online. So all the registered learners to this NPTEL course, Mathematical Methods and Techniques, have access to MATLAB Online and have access to these set of toolboxes. So I have a work live script for you to practice along with me today. So I'm sharing the work script in the chat. So this work script has placeholders to enter the code, which we will do together during the hands-on activity. I'll explain what to enter and each step what we are trying to do. So I'll share the work script in the chat. Please download the work script. So I have posted the work script in the chat. So this work script will be useful to practice along with me during the hands-on activity. Please download the work script to your device, and during the session I will post the codes in the chat as well so that it is easier for you guys to follow along. And at the end of the session, I will share the solution live script for your future reference. So next, we'll see how to access MATLAB online provided for this course. So for that, you can go to the NPTEL course page, Mathematical Methods and Techniques in Signal Processing. Go to the NPTEL course page for the course in Mathematical Methods and Techniques and scroll down to a section called MATLAB. The course outline section, go to the section MATLAB, where you will see two options, MATLAB Access and MATLAB Training. Click on MATLAB Access. Here you will see a series of steps to access MATLAB online for this particular NPTEL course. So first thing you will need is to have a MathWorks account. If you don't have a MathWorks account, please click on the link which is mentioned in step 1. MathWorks account, create one here. Please click on that and create a MathWorks account. Once the account is created, you can go to the link provided in step 2 to access MATLAB for the NPTEL course. So I'm clicking on step 2 link here, which will take you to the MATLAB license link. So here in this page, click on Access MATLAB Online. So once you click on this link, Access MATLAB Online, you will redirect to the MATLAB Online page, which you can confirm by seeing the URL here. It should show matlab.mathworks.com. Now click on Open MATLAB Online. Again, confirm if you are on the right page. The URL should say matlab.mathworks.com. I hope everyone could open the MATLAB online page. Now we will add the work script which we will be working on today to the MATLAB drive. So for that, you can expand the left section of your MATLAB online which says Files section. So to upload the work script which you have downloaded sometime back, right click on the Files pane. Right click on the Files pane and select on Upload Files. Select Upload Files. Now locate the work script which you have downloaded sometime back. Select the work script and click on Open. This will upload the work script to the MATLAB drive, and once the uploading is completed, it will show uploaded one file 100%. Once you get this message, you can click on OK. Now we locate the work script which we uploaded to your MATLAB drive and open the work script. So double click on the work script which you uploaded right now. and it will open the work script, work underscore mathematical methods underscore sampling.mlx file. So this is the work script which will be working for the hands-on activities to solve our engineering problem. And this is a live script. To make you familiarize with the live script environment, live script is a interactive script, MATLAB script, where we can embed code snippets, text and images in one environment. To make, we have on top tabs like home, plots, apps, live editor. So this is called tool strip. And on the left, you can see the files pane, and below you can see the workspace. So here in the live script, we have the table of contents. So for easy navigation to different section in the live script, the table of contents here is linked to different sections in the live script. So you can click on a specific heading to redirect to that specific section in the live script. So reiterating the engineering problem we are trying to solve today. So the engineering problem was, how can we convert audio signals between different sample rates without introducing distortion or artifacts while ensuring efficiency and fidelity? So as a first step, as I mentioned, we'll go through three different scenarios. The first scenario is downsampling a signal, that is reducing a sampling rate of a signal. So the scenario here is, let's consider we have a audio signal. We have a drum sample recorded at 48 kilohertz. And you want to use that particular audio signal to a project at 16 kilohertz. Let's say to save memory or match with an old hardware. So the drum signal here has two tones, one at 4 kilohertz and the other one at 10 kilohertz. So what is the scenario we have? We have a drum sample which is recorded at 48 kilohertz. We want to convert that 48 kilohertz drum audio signal to a lower sample rate which is 16 kilohertz. So for that, first let's generate the drum signal with two tones, one at 4 kilohertz and another at 10 kilohertz. So first let's define the sampling rate, the original sample rate. Let's define the sample rate as Fs high equals 48 kilohertz. I'm posting the code in the chat as well for your reference. So we have defined the original sample rate as Fs high 48,000. And what is the target sample rate? Let's say it is Fs low, which is 16 kilohertz. And we'll define a time vector to generate our drum audio signal. Let us call that as T equals one by Fs high, which is our original sample rate, within a range of 0.5. So we have defined a time vector that spans from 0 to 0.5 seconds, which increments based on the original sample rate, which is 48 kilohertz. So this vector will be used to generate the drum signal. Now, as a next step, we are going to generate the drum audio signal. Let's call that signal as drum sig equals. We'll generate a drum signal with two tones. So first tone is at 4 kilohertz frequency and the second tone is at 10 kilohertz frequency. So we have defined the original sample rate, the target sample rate, and we have defined the time vector to generate the signal. And also we have defined the signal, required audio signal, the variable drum sig with two tones, one at 4 kilohertz and the another one at 10 kilohertz frequency. Now let's visualize the drum signal which we generated. Let's visualize in the frequency domain so that we can visualize the frequency component using the function P spectrum. So the next line is we are visualizing the power spectrum of the generated drum signal. Let's run this particular section and see the results. So for running a particular section on LiveScript, go to the Live Editor tab and navigate to the section and locate Run Current Section button in the Live Editor tool strip. Locate the Run Section button and click on Run Section. So here you will get the original two-tone signal spectrum. So here you can see there are two clear peaks, one at 4 kilohertz and another one at 10 kilohertz frequency. So we have generated the required drum signal for our engineering problem. Now the next task is to downsample the drum signal and visualize the power spectrum of the downsample signal. So for that, first step is to compute the conversion factor. So since we are reducing the sample rate, let's compute the downsampling factor here. So to compute the downsampling factor, we just divide the original frequency with the target frequency. So we'll call it as down factor for computing the downsampling factor or conversion factor. We'll divide Fs high divided by Fs low. Now we will downsample the signal. Let's save that to a variable drum down. And the function for downsampling the signal in MATLAB is downsample. So the downsample, the first input is the required signal which we need to downsample or reduce the sampling rate. And the second input is our downsampling factor which we computed in the previous step. So we have downsample the signal. Now, to visualize the spectrum of the downsample signal, have used the same code as we used for visualizing the original signal spectrum using the function P spectrum of drum down, which is our downsample signal with the frequency with the new target frequency. Which is Fs low. Let's run this section and analyze the results. Click on Run section. So here, if you analyze the figure or the results, this is a downsampled version of the original drum signal, which had two tones, one at 4 kilohertz and one at 10 kilohertz. So here, the downsampling is done without applying any anti-aliasing filter. So what do you see here? We see a peak at 4 kilohertz, which is as expected because the original signal also had a peak at 4 kilohertz. And we also see a peak at 6 kilohertz. So what is this peak at which is shown at 6 kilohertz? This is not something which was there in the original drum signal. So how does this 6 kilohertz come into picture when we downsample the signal? So what is happening here is the original signal had a tone at 10 kilohertz. So the 10 kilohertz tone, which is above the new Nyquist frequency, when you downsample this 10 kilohertz component aliases to a lower frequency. So there is a alias tone which is not necessary which was not expected in the downsample signal, which is appearing as an aliased frequency at 6 kilohertz, which is actually affecting the quality of the downsampled signal. So how do we remove this extra frequency tone which is appearing at 6 kilohertz? So the problem here is aliasing. So if the original audio contained frequency component which is above a Nyquist frequency. So here in this example, the new Nyquist frequency is 8 kilohertz. So when you downsample to 16 kilohertz without filtering, these higher frequencies will be aliased and it will be folded back into the audible spectrum, which appears to be like a distortion or unpleasant frequency component. Now, how do we get rid of this extra tone or extra aliased frequency component? The solution is to use an anti-aliasing filter. So we will see how we can remove the extra component which appeared in the downsampled signal using an anti-aliasing filter. So for that, we will apply a low pass filter to remove these frequencies which is above 8 kilohertz, the Nyquist frequency, before downsampling. So in the next task, we will apply a low pass filter to remove this frequency. And the cutoff frequency for this low pass filter should be equal to or below the Nyquist frequency. So we will save the low pass filtered signal to a variable called drum filter, and we will use the function called low pass to apply a low pass filter to the drum signal with a cutoff frequency of 8 kilohertz. Now, as a next step, after applying this filter, we will downsample the signal. Let's call that final downsample signal as drum filter down. And we will use the same function for downsampling, which was downsample off. Now, the first input is not the original drum signal, but the filtered drum signal. Drum filter. The downsampling factor was down factor. Same as we did in the previous task. So what we have done in this step, we have applied a filter. We have applied a low pass filter to the original audio signal, and then we have applied the downsample function. Now let's run this particular section and visualize the spectrum to see if there is any change for the downsample signal without applying an anti-aliasing filter and after applying anti-aliasing filter. So here you see that there is still some presence of frequency at 6 kilohertz, but the intensity or the power per frequency is being reduced. When you compare it with our previous result, the 6 kilohertz power or frequency, power per frequency is being reduced after applying an anti-aliasing filter. So here we see a 4 kilohertz tone is preserved as expected, the original tone, and the 10 kilohertz tone which is above the cutoff frequency is significantly attenuated by the low pass filter but not completely removed, because the real world filters are not like an ideal filter which has an ideal transition band. So there is some presence of uh, tone at 6 kilohertz frequency. But now, can we make this anti-aliasing filter more effective to reduce the effect of 6 kilohertz tone? So for that, we will design a much more efficient low pass filter with, let's say, increased steepness factor. There are different filter specification. So let's try it out with a new filter, new low pass filter with increased steepness. So in the next task, we are going to use a new low pass anti-aliasing filter, which is having an increased steepness value. So let's call that filter as drum filt 2. So here we have increased the steepness value to 0.95. And now using the new designed filter, let's downsample the filtered signal and see the results. We will use the same downsample function. Let's run this function section. So when you visualize the power spectrum after using a much more efficient low pass filter, the effect of 6 kilohertz is even more decreased. Now the power per frequency or dB is somewhat around minus 60 or minus 70 dB, which is much more lower than the previous low pass filter. So likewise, if you design a low pass filter which is more closer to the ideal situation, ideal filter, we can even more reduce the effect of aliasing tone, which is at 6 kilohertz frequency. So to see the comparison of a different low pass filter, I have here a different higher order FIR filter which I have defined a particular passband frequency which is lower than the cutoff frequency and also a stop band frequency, and we will downsample the signal using the new low pass filter. Let's run this section and see the result. So here you see that with a higher order FIR filter, the alias tone at 6 kilohertz, the effect is even more decreased and the power per dB is somewhat around minus 160 dB, which is very negligible and can be neglected, and it won't affect the quality of the downsample signal. So this is how the effect of filtering affect the downsampled signal. So when you need to downsample a signal by an integer factor, so here right now we have seen the down example of 48 kilohertz to 16 kilohertz with a down factor of 3, which is an integer. So in MATLAB, we have inbuilt function for downsampling, which is the decimate function. So what does this decimate function in MATLAB does is, it automatically applies a high quality anti-aliasing low pass filter before downsampling. So as previously what we have done is we have designed a low pass filter, we have applied that low pass filter and then downsampled. So instead of that, in MATLAB we have a built-in function called decimate, which will automatically applies a high quality anti-aliasing low pass filter before downsampling. So let's try it out, that decimate function, and visualize the spectrum. So for that, we will downsample the signal, our original signal, and save it as drum des with the function decimate. So decimate of drum sig with a downsampling factor which is saved in down factor. Let's visualize the spectrum for this downsample signal and analyze the results. So after applying the decimate function, we see that we have a clear tone at 4 kilohertz and we have a small tone at 6 kilohertz. So here what happens? It automatically, the decimate function automatically applies the anti-aliasing filter, and hence the 10 kilohertz tone is automatically filtered out by the internal anti-aliasing filter. So the effect of aliasing is less when compared to the previous methods we had. So this is the first scenario where we see what is the impact of filter when we are reducing the sampling rate for an audio signal. Now we'll move to the second scenario where we have to upsample a signal. So upsampling a signal means increasing the sampling rate. So consider for this particular upsampling signal, consider another drum signal which is, let's say, recorded at 16 kilohertz, and now you need to use this audio in a modern session which is running at, let's say, 48 kilohertz. So this is a clear example of upsampling where you have the original signal at 16 kilohertz and you need to resample the signal to 48 kilohertz. So we will see what is the effect of upsampling without applying a filter, and after applying filter, what will be the result of the upsample signal. So for that, first let's generate the drum signal. So here we are considering a drum signal with a single tone at 4 kilohertz, and we'll first visualize the spectrum of the drum signal. So first define the original sample rate as Fs low equals 16 kilohertz, and the target sample rate, let's say Fs high, equals 48 kilohertz, and the time vector t equals, which is spanning from 0 to 0.02 seconds. With increment of our original sample rate 1 by Fs low. And we will generate a second drum signal which has a single tone at 4 kilohertz. Let's call it as drum sig 2, and we'll initialize the spectrum. Let's run this section. So we have a clean peak at 4 kilohertz and nothing above the Nyquist frequency, nothing above 8 kilohertz. Now we will upsample this drum signal and then visualize the power spectrum of the upsample signal. For that, as we did for downsampling, we'll first compute the upsampling factor. First, we'll compute the upsampling factor and then upsample the signal. Let's save the upsampling factor to a variable up factor. And for upsampling the signal, we have a function called upsample. Upsample of our new drum signal with a factor of up factor. Let's run this section and visualize the spectrum. So here what you see is a peak at 4 kilohertz, and you see multiple other peaks also which is having a same power range as that of the original tone at 4 kilohertz. And these extra tones, which you can see at around 12 kilohertz and one at 20 kilohertz, is called spectral images. So this happens because of imaging problem. So what happens when you upsample a signal without proper filtering is the spectrum now shows images or copies of the original spectrum, which is centered at multiples of the new Nyquist frequency. So these images are considered as unwanted artifacts and can cause distortion or unnatural sound if you play back or process further. So it's important that you need to will have to remove those images from the signal spectrum. So to properly upsample a signal and to avoid unwanted spectral images, you must apply a low pass filter after zero stepping. So after upsampling, you need to apply a low pass filter to the upsampled signal. So this is to avoid the unwanted spectral images. And this particular filter is called interpolation filter. And this filter should have a cutoff frequency of the original Nyquist frequency. In this case, 8 kilohertz for a 16 kilohertz original sample rate. So let's apply a low pass filter to our upsampled signal. Let's call it the new signal as drum up filled. We are going to apply a low pass filter. To the upsampled signal, and the cutoff frequency is Fs low by 2, which is our original Nyquist frequency. And the target frequency Fs high. So when we downsampled the signal, we already saw the selection of a low pass filter. So we saw that when we increase the steepness of the filter, the spectrum was showing much improved results, was giving much improved results when applying increased steepness low pass filter. So we will directly use an increased steepness value for upsampling for this interpolation filter. Let's use the same value for steepness as 0.95. And let's visualize the spectrum. So this is a spectrum of a signal, of an upsampled signal with low pass filter. So if you compare the results before filtering and after filtering, so before filtering or without filtering, applying an interpolation filter, the effect of spectral images at 12 kilohertz and 20 kilohertz was very comparable to the original tone at 4 kilohertz. So after applying an interpolation filter, what we see is the effect at 12 kilohertz and 20 kilohertz is much reduced. So the spectral images is much reduced when we apply a low pass filter or an interpolation filter. So here what happens is the low pass filter removes the images above 8 kilohertz, which includes the spectral images created by upsampling. Now the signal is having a smoothly interpolated between the original samples and the reconstructing the waveform as it would appear at the higher sample rate. So as like downsampling in MATLAB, we have an inbuilt function to upsample the signal, which is interp, interp. So this function automatically applies an appropriate low pass filter or interpolation filter to remove the spectral images created by upsampling. So there is no need to apply a low pass filter manually after upsampling the signal. So we will try that out with the function interp in MATLAB, and let's call that new signal as drum up filled 2. The function is inter p. The first input is the signal which we want to upsample, and the second input is our conversion factor, which is saved in up factor. So let's run this section. So here we see that with the built-in MATLAB function interp, we have reduced the effect of 12 kilohertz or 20 kilohertz, which is nothing but our spectral images. And we see that there is a strong clear peak at 4 kilohertz as expected, the original tone. And most images above 8 kilohertz are removed by the inbuilt filter in the interp function, and the spectrum is much cleaner than simple upsampling. So what happens when we apply the interp function is it first upsamples the signal by inserting zeros and then applies a designed low pass filter with a cutoff frequency at the original Nyquist frequency. So this process suppresses the spectral images that would otherwise appear above 8 kilohertz. So this is the second challenge we had on how can we upsample or increase the sampling rate of an audio signal correctly by choosing a low pass filter with appropriate filter specification and appropriate function for upsampling. Now, the third scenario what we have is arbitrary resampling. So till now, the upsampling and downsampling, which the scenario which we explained, was integer sample rate conversion. But in real world audio and signal processing, it's not mandatory that you will have an integer sample rate conversion. You often need to convert signals between sample rates that are not integer multiples of each other. So for example, you might receive an audio at let's say 48 kilohertz, which is very common, this particular 48 kilohertz frequency, which is very common in video production. But need to deliver it at a frequency of 44.1 kilohertz. So this 44.1 kilohertz is very common. If you relate to a real life example, it's very common for an audio CD and many streaming platforms. This is the standard frequency range, 44.1 kilohertz. So the scenario here is we have a signal at 48 kilohertz and we need to resample that signal to match up with a hardware which is working at 44.1 kilohertz. So this scenario is called arbitrary resampling the signal. Now, if we apply simple upsampling or downsampling methods like we did in the previous activities, like functions like upsample, downsample, or decimate or interp. So this will work only for integer ratios. So for arbitrary ratios, you need a method that can accurately convert between any two rates without introducing artifacts such as aliasing or imaging. So here the problem or challenge is how do we convert a signal from one sample rate to another when the ratio is not an integer. And the condition is we need to preserve audio quality and avoid artifacts like images or alias tone. Now, as a solution for this problem, MATLAB has a function called resample function. So what happens in this resample function is it performs the process in 3 different steps. So in backend for this resample function, it happens so that first it will upsample the signal by a factor of let's say p, and then it will apply a filter which can be an interpolation filter or anti-imaging filter, and it can also act like an anti-aliasing filter, so that it removes both the impact of images and alias tone, like how we saw in downsampling and upsampling. And after this process, the resample function downsample the signal by a factor of q. So this resample function works in 3 steps. First, it upsamples the signal, and then it applies the appropriate filter with appropriate filter specification, and then it downsample the signal by a factor of q. So now this ensures high fidelity and artifact-free conversion between any 2 sample rates. So we will see how we can use the resample function. So let's take a signal, for example, which is having a single tone, let's say at 1 kilohertz tone, and let's convert that signal from 48 kilohertz to 44.1 kilohertz frequency. So let's define the original sample rate for this example as fs. Let's say fs in equals 48 kilohertz, and the target sample rate, which we can save it as fs out into 44.1 kilohertz, and let's define the time vector t equals 0 is to 1 by fs in, which is our original sample rate, the span of 0.1. And we'll generate tone, a single tone frequency for the demo purpose. Let's call it as mixed signal equals sine of. Same way how we generated our previous audio signal. Only difference is now the signal has a single tone at 1000 hertz. Time vector t. Now for resampling, we need to calculate the conversion ratio. So to calculate the rational conversion factor, and we will save it to a variable p and q. And the function to calculate the rational approximation or conversion factor is RAT function with an input of our target sample rate fs out by fs in, the original sample rate. So this is how you calculate the rational approximation factor. Now we will apply the resample signal. We'll apply the resample function. Let's call that resample signal as mix sig resample. Resam equals, the function name is resample, and the first input is our generated mixed signal, which is having a single tone at 1000 hertz, and the resampling factor, which we calculated in the previous step as P and Q. And we are visualizing the spectrum to analyze our results. Let's run this section. So here we have plotted two spectrum. This is our original signal spectrum before resampling. So it had a single tone at 1000 hertz or 1 kilohertz. And after resampled spectrum, with a new target sample rate of 44.1 kilohertz. This is the resample signal spectrum we received. So what you see here is you have a main peak at 1 kilohertz as expected, which need to be preserved as well after resampling. And above the Nyquist, you see very low skirts or noise above the new Nyquist frequency, and very low level content above 22.05 kilohertz, which is our new Nyquist frequency. And this is not actually true imaging or aliasing effect. So it's filtered out. The effect of imaging or aliasing is filtered out with an inbuilt or automatically filtered out using the resample function. And if you analyze the power per frequency range, it is at the range of uh, below 60 dB. It's around minus 60 to minus 90 dB, which is very low when compared to the main main tone at 1 kilohertz frequency. So there is no strong images here after applying resampling. And this is because we have used the resample function. So the resample function automatically handles the complex filtering and rate conversion. So the output has correct sample rate with no aliasing or imaging. And the tone remains at 1 kilohertz, but the sample rate is now the new target sample rate, which is 44.1 kilohertz. So hence we come to the end of the session of resampling methods in MATLAB. We saw how we can convert audio signals between different sample rates and why resampling is important, and what happens if we select an improper sampling rate conversion or improper technique for sampling a signal, and how it affects the quality of the audio signal. So in the work script as well as in the solution script, I have added some additional resources also, which is our MATLAB examples, or it can be some documentation examples as well. So you can refer to these additional resources to understand more about resampling and about multi-rate signal processing and how we can reconstruct the missing data using MATLAB functions. So I will share the solution live script as well in the chat so that you can refer to the solution later. So detailed description for each section, for each code is explained in the solution live script, and also you will find these additional resources in the solution live script as well. So just to summarize what we did in today's tutorial. So we had an engineering problem on how we can convert signals between different sample rates with a constraint that we need to avoid distortion or artifacts, but still maintain efficiency and fidelity. And this was the engineering problem we tackled today in MATLAB. And these were the observations on a high level. So we see that, or we infer that always we need to filter before downsampling and after upsampling. And it's always recommended to use built-in functions in MATLAB like decimate and interp and resample to simplify the process and reduce the risk of artifacts. And whenever we resample the signals, it's always important to analyze the signal spectrum. That is important to visualize the signal in frequency domain using functions like p spectrum. So this will help to verify the unwanted frequencies if there is a presence of aliasing or imaging, which we need to tackle. And it's also important to visualize the spectrum to understand the signal's integrity is maintained after sampling, whether it is upsampling or downsampling, or it can be arbitrary resampling. Hence, we come to the end of today's tutorial. Thank you all uh, for listening to this session.